All right, group number 1. According to the data for magnesium and calcium, do metals get more reactive or less reactive as you move down the periodic table? More reactive, good. And what made you say that calcium was more? I'm just going to time out real quick. Can everyone else put their cell phones away? And if you don't need a computer screen, which I think you just need a lab packet, I'm getting a little suspect in here. It smells a little like amines and bases here. Okay, so group 1. You said it gets more reactive as you go down. What made you say calcium was more reactive than magnesium?
It had more kind of like a white stuff come out like the top of it.
Yeah, that chalky white stuff. And what was causing it to come out of the test tube? Were you tipping it?
No, it got really hot.
Right, it got really hot. Let's talk about what was potentially happening there. This might be one of the reactions you want to write somewhere off to the side. I'll go ahead and just do calcium. So calcium is a solid metal. And was this one that you were reacting in acid? Yeah, this was the acid. So that was what, HCl? That is an aqueous solution. Anytime we have a single element by itself, does anybody remember what type of reaction that could be? We saw it with the metal non-metal lab. We saw it with the sodium and the potassium. A single element by itself that could swap places with another one. Anybody remember what SR stands for? Single replacement. They're going to singly replace each other. Calcium is a metal or a non-metal? It's a metal. Even though H is not a metal, would you agree it's on the metallic side? It's on the same metal side, so they could potentially swap places. So then calcium would be joined up with chlorine. Next unit, we'll check these charges. Calcium in column 2 is a +2. Chlorine is in column 17. It's a -1. That's not balanced, so I need 2 of these. We'll put a little 2 there. That's that chalky white substance you were seeing form, that calcium chloride. And then H would pop out by itself, and H has to be diatomic because that's what the periodic table says so. So from this equation, Kalina, can you tell me what that gas was that was coming out of the test tube, causing that white solid to rise up, based on what we have written up here? Is this a gas? No. Was the acid a gas? No. Is this compound a gas? No. Yeah, it was the hydrogen gas. Yeah, so those bubbles would be hydrogen gas. We could bubble them up or collect them in a test tube, light them on fire, and do a hydrogen test there. So again, you'll see single replacement reactions pretty much till the end of the year. That's one of our 5 types of reactions, so that's pretty common. I'll leave that up there. Group number 2. What happens as you go left to right on the periodic table? Like as you went from magnesium over to aluminum? It gets less reactive. Good. And what made you say aluminum was less reactive? Right, nothing really happened. Now, part of that, I would definitely think aluminum could react with the hydrochloric acid, so that there's a chance maybe the acid just wasn't concentrated enough, or sometimes aluminum just sitting out in the bottle kind of rusts. Now, it doesn't look like rust because it's not iron oxide, but aluminum oxide forms kind of a clear layer surrounding the aluminum, so there's a chance that it had a protective surface on the aluminum. So one way we could test for that is just scratch that aluminum piece and then put it in the acid. I have a feeling if you did that and exposed some fresh aluminum, you might get a little bit of bubbling. Definitely not as much as the magnesium, just like you guys were saying. Good. So, any questions on station number 1? Metals get more reactive as you go down the periodic table, less reactive as you go right. Well, that's at least what we saw when they were reacting with acids. Let's see what happens when they react with water. So, group 3, how do the elements compare in reactivity as you move down the periodic table?
It's more reactive.
Definitely gets more reactive. How did you know potassium was more reactive than sodium, or calcium was more reactive than magnesium? What made you say that they were more reactive?
I guess the fact Potassium caught on fire.
Yeah, potassium caught on fire, whereas the sodium just kind of sputtered around. How long did it take the potassium to react?
6 seconds.
Whereas sodium took,
44 seconds.
right, so yeah, the potassium was a much faster reaction. Good. Group number 4, actually, yeah, Tobin, we'll let you answer this. How do the elements compare in reactivity as you go left to right across the periodic table?
The reactivity down.
Yeah, the reactivity went down. They became much less reactive. There's a reason why I did the sodium and potassium, and then you went on to do the magnesium and calcium. There's no way that I'd let you put those two in water. Now, any guesses? Well, no, we'll go on to question 5 here. So group 5, how does the pattern of reactivity with water compare with the reactivity of acids? It's the same. So no matter whether they're reacting with water or reacting with acids, it doesn't seem like this is a coincidence. Going down the periodic table, they get more reactive, and going left to right, they get less reactive. Now, sometimes people were comparing the reaction in acid versus the reaction in water. The only two comparisons that we would have for that would be calcium and magnesium. Did anybody have to say anything about acids versus water? Which ones were more reactive? Or we could do it right now. Which would you say was more reactive? The reaction in the acid or the reaction in the water? Thumbs up the acid, thumbs down the water. And again, you'd have to look at the magnesium and calcium results because those are the only two metals that we tested in both solutions. Yeah, I would probably think the acid reaction would be a little bit more vigorous. There's a reason we did not test sodium and potassium in acid. If that was what the reaction looked like in water, you can only imagine what it would look like in that acid. And yeah, you don't want to get those metals anywhere near that acid. Good. So yeah, some people might have said the acid reaction was more reactive than the water acid. Or sorry, the water reaction. All right, so let's come up with a theory for this, kind of like our Pogel activity. Group 6, based on their core charges, would you expect metals to gain or lose electrons when they react? Okay, they are positive. Sodium and potassium both had core charges of what? 1. +1. Magnesium and calcium were? +2, and if maybe we want to take a look at aluminum over here, that was a +3. So they are positive. They would be attracted to negatives. How do you, what is your impression of those positives? Are they big positives, small positives?
They are pretty small.
Yeah, they're pretty small positives. So is there a big attraction pulling electrons into the atom? Probably not much. And is there a lot stopping us from ripping off their 1 or 2 electrons? No. So do you want to revisit that answer? Yeah, I would probably think that a +1, +2, maybe even a +3 is probably going to lose electrons. Because there's not a lot of positive charge holding on to the electrons that you do. Question number 7. Let's use some atom models to explain this. We want to know why larger metal atoms are more reactive. So, group 7, what 2 elements did you pick for this?
Sodium and potassium.
Yeah, let's do sodium and potassium. How would you draw sodium?
+1 in the middle with 3 waves around it.
Yep, 3 energy levels. And here's this electron we're trying to rip off. And potassium would be a 1+ with 4 energy levels of electrons. And here's this electron you're trying to rip off. Can you tell me why it's easier to rip off the electron from potassium?
Because there's more space in between the 2.
Right, and what does Coulomb's law say about larger distances between charges?
Less energy to be able to remove.
Right, there's less attraction here, which means there's less ionization energy. It's going to be a lot easier to rip off that electron. Whereas even though a +1 isn't super strongly attracted to a negative, it's at least closer, so it will have a stronger attraction here, so it'll take more ionization energy. So it seems like our theory from the Pogel activity totally explains why potassium was more reactive. Any questions on it? Let's see if it also does a good job explaining what happens as we go right on the periodic table. So what two models would you want to pick for this, group one? Question 8. Calcium and potassium?
Yeah.
All right, so I'm going to leave the potassium up there. So now, now we just need to draw calcium. How's calcium's model going to look different than potassium?
Plus
2 plus? Is that what you just said?
Yeah.
Okay, yeah, 2 plus with 4 rings?
Yeah.
Yep, I agree. And here's this electron we're trying to rip off. We said potassium was more reactive, right? So why was it more reactive?
Because it took less energy.
Yeah, it took less energy. Why does it take less energy?
Because there's more attraction.
There's more attraction in calcium? Yeah, there's more attraction between a +2 and a negative than a +1 and a negative. So this is still a really weak attraction here, whereas calcium has 2 times the attraction because it's a +2 charge attracting that negative, so it'll take more energy to ionize, more ionization energy. Yeah, it seems like Coulomb's law totally explains that trend as well. And what would be even harder to react than calcium? Well, if you go all the way over to gallium, just like we went over to aluminum, that would be a +3 core charge. So that'll be even harder to rip off those electrons. Sweet. Any questions on that? Now the cool thing is we have an activity series on the back of your periodic table. So I can go ahead and pull that up on the screen real quick here. You might want to pull yours out as well. So if we focus on this activity series, the 4 elements or 5 elements that we were looking at were potassium, calcium, sodium, magnesium, and aluminum. How does this activity series compare with what you saw in the lab? Group 2.
Like the potassium is like the second most common, like that reacting fastest.
Right, potassium was like the fastest reacting element that we saw, the most dangerous element we saw, and that's towards the left of the list. Now, does it tell you the left side of the list is the most reactive? No, but that's just something that you're going to have to know when you look at this list. And out of all the elements that we looked at, would you agree aluminum was the least reactive? Aluminum didn't even really do anything when we put it in the acid. So this is definitely an activity series which is related to reactivity. And is it any surprise that you'd find elements like copper, silver, platinum, and gold at the end of the list? If you're wearing gold jewelry, do you want that dissolving and rusting or oxidizing while you're wearing it? No. So again, that end of the list would be the least active side. Quick conversation in your small groups. Based on what you just learned about going up and down the periodic table, is there anything that's a little bit surprising about this list? Quick conversation. I'll open it up to the whole group. Is there something that's surprising up here? Something that you would not expect to maybe be as reactive as what it's saying it is? Potassium was more reactive than sodium. You would expect sodium to be more reactive than Lithium, right? Lithium is a small atom, so the electron is going to be super close to the positive one charge. According to our little atomic models, we would think lithium would be less reactive than sodium and less reactive than potassium. But this is saying it's the most active element on the periodic table. It is, and that's why it's called the activity series. So maybe you just want to put a note in your post lab here that activity is a little bit different than reactivity. We're defining reactivity based on how fast the reaction occurred, or how much gas was produced, or how quickly it caught on fire. So that is one sign of a chemical change. That's one way to measure reactivity. This list is based on electrochemistry. So we're not really going to even scratch that surface probably until AP chemistry. There's a whole chapter or unit in AP chemistry on electrochemistry. So this activity series is based on electric voltages when atoms are gaining and losing electrons. So this is based on reduction potentials. And lithium does have the highest voltage, which means it has the highest push behind those electrons. That might not necessarily correspond to a spectacular explosion up here. So it kind of depends on how you define reactivity. We're defining it based on our observations in the lab. If you're going to hook them up to voltage meters and measure the voltage given off as they're reacting, lithium would probably take the prize. So basically what I'm saying is there are multiple answers that you could put down as far as that, I think, last or second to last discussion question. What's the most reactive metal on the periodic table? Well, according to this, so yeah, you could go with lithium, but that might not go with what you predicted at the end of the post lab. Any questions on that? All right, let's take a look at question number, I think we're done with station 2. Yep, that was it. Any questions on number 9? All right, on to station number 3. Usually students find this to be the most challenging, so it might take us a little bit of time to go through this, but once you get it, I think you'll get it. So just to review, in station number 1, or reaction number 1, I put sodium bromide, a sodium bromide salt solution, in with chlorine, and I asked myself the question, will they swap places and produce bromine? Would you agree in station number 1, the top layer was orange? So that told us, if we look above there, hexane layer is orange, tells us bromine is by itself, which that by definition is the less reactive element. It's okay sitting by itself. And that made the chlorine, by default, more reactive. And then the last question we had to ask ourselves is, did I start with bromine or did I end with bromine? And in this case, the bromine who is by itself had to react to produce that bromine. So this reaction definitely did occur. So I can put a little check mark rather than a question mark there. All right, I think we are back to, I forget where I left off. Let's go back to group 1. So reaction number 2 here. What color was the top layer? Magenta, okay, yep. And that tells you which element is by itself. Iodine, yep. Where are you going to eat tonight? Are you going to Moe's? Papa John's? You said iodine. I was just wondering where. Okay, so it is iodine. That tells you which element is more reactive.
Chlorine?
Chlorine, yep. And now the question is, did you add the iodine to this test tube or did you produce the iodine in a reaction? Did the reaction occur?
Yes.
Yes, because here we did not start with iodine. We started with the iodide ion and you produced iodine by itself. So therefore that reaction swap did have to take place. And you'll notice these are single replacement reactions, just like we saw before. Any questions on reaction 2? All right, group 2. What about reaction 3? What color was the top layer? Orange? That tells you which element is by itself. Bromine is less reactive. Who was more reactive than bromine? Chlorine. Good. And when we piece that together, did we start with the bromine or did we have to react to produce the bromine? Right, we started. You were the one that added this bromine and it never turned clear So therefore, this reaction never occurred. So that reaction, it was a potential reaction. That's why there was a question mark there. But that reaction did not occur. Why? Because the less reactive bromine was already sitting by itself. It doesn't want to react, so therefore it's not going to react. Any questions on station 3? You'll see station 3 and station 1 are complete opposites of each other. We took a bromine chemical and reacted it with chlorine. It reacted. If we flip-flop that reaction and try to react bromine with a chlorine compound, it will not react. Because in this case, we're saying bromine is less reactive. You can't flip the order and then say chlorine's more reactive. So bromine is still less reactive. So therefore, in this reaction, the reverse reaction will not occur, but the forward reaction will occur. So technically, we probably could have scrapped 3 out of the 6 reactions, but I like people to see one reaction going this way versus the reverse. If one of them works, the opposite reaction would not work. I think we're up to group 3. What happened in number 4?
There's like a
Magenta top layer, yep. That tells us what is by itself. Iodine, good. Less reactive than which element? The bromine, good. And did we react to produce the iodine, or did you put in the iodine? Right, it reacted to make on the right-hand side of this reaction. This is what you added. The reaction produced that iodine, so yes, that is a chemical reaction there. Any questions on number 4? It seems like it's going pretty smoothly. Period 2 had some trouble with this, but I think maybe just because we had some extra time, got our questions answered a little bit better. Yeah, this seems like it's going well. Tobin, what about station 5?
Top layer, I got layers.
Pink? Yeah, magenta?
So, iodine was less reactive.
Yep.
Was more reactive.
Chlorine is more reactive. Did this reaction occur?
Iodine.
No, because you were the one that added the iodine to the test tube. It never cleared up, so it never produced chlorine, so this reaction did not occur. And this would be the complete opposite of number 2. Number 2 did react, saying iodine was less reactive than chlorine, so now if iodine is by itself, it's not going to want to react with the chlorine. So the iodine is just going to sit there by itself. And then group 5, what about number 6? Pink or magenta, yep. Telling us which element is by itself, which is less reactive than bromine. Did the reaction occur?
no.
No, because you were the ones that added the iodine. It's not going to want to react if it's less reactive, so it sits there by itself. No, and you can see number 6 is the complete opposite of number 4. Questions on that? So these are usually some questions that trip some people up on the quiz, so let's make sure we are good to go with this. So again, Google Docs got a little bit weird when it opened this file. There should be an arrow with a question mark there, because we're not sure. If this single replacement reaction does occur, this is what the swap would look like, but we don't know whether that swap will take place. So group 6, what did you say about this first reaction? We'll call it A. Did it occur?
Yeah,
Okay, and tell me why.
because the chlorine was on the top and it went
Right, chlorine is more reactive. Here it's sitting by itself. It doesn't want to be by itself. It wants to react as a chlorine compound. And bromine is less reactive. So yeah, it's going to want to swap to get the bromine by itself. Good. Any questions on that? Group 7, tell me about the second reaction, or letter B up here.
It would, the bromine would want to be with the potassium and the iodine would want
Right. Because bromine is more reactive, and iodine wants to get by itself because it's less reactive. So yes, that reaction will have to proceed. And back to group 1, what about letter C? Yes? Okay, which would tell you which element is less reactive up here. If this reaction occurs, who's sitting by itself at the end? The chlorine, which tells you chlorine's less reactive. And when you take a look at your data table on the previous page, how often did you write down that chlorine was less reactive?
not
Not once. It is not less reactive. So you're going to cross this out because, again, chlorine is more reactive. So it wants to be reacted in a compound, whereas the iodine is less reactive. It wants to sit by itself. So if it's already sitting by itself, it will not singly swap with the chlorine. So yeah, that reaction would not occur. Questions about how we figured that out? I can guarantee there's going to be like 2 questions like this on the lab quiz and on the test. We're good to go. From this information, I think we are on to group 2. Totally lost my train of thought. Which of the halogens is the most reactive? Oh, that's not sure. All right, group 2. Which is the most reactive halogen? Hey, Belle. I'm awkwardly waiting for an answer. Group 2, question 11. So here's this periodic table. Johnny's done changing in the back room there, so yeah, you can take this all back there and work in the back room. Just right back here. Group 2. Yule, which one's most reactive? Chlorine. There we go. Based on their core charge, would you expect halogens and other nonmetals to lose or gain electrons when they react? Group 3. I'm going to have to edit this video. So at 26, 27 minutes, I'm just going to have to like chop out my lesson. Okay. Okay, because halogens have what sort of core charge? Oh, which one? Yeah, it's a high core charge. We're talking like a 7+. I don't know how many rings we want, but yeah, it's going to be super attracted to that negative, and halogens do have room for electrons, so yeah, I would totally think that they would gain electrons. Well, that's the opposite of what we said for metals. Is this the first time that we've seen nonmetals have an opposite property of metals? No, metals lose electrons, nonmetals gain electrons. Let's explain why chlorine is more reactive than iodine. I think we're on to Group Tobin.
Chlorine is more reactive than iodine because it takes less energy to react.
Not quite. So let's get an atomic model for chlorine up here. You're on the right track. Chlorine is going to have what core charge? Column 17? 7+. How many rings of electrons? 3. And are we losing electrons or gaining electrons? Yeah, so here's this electron we're trying to steal. And iodine would be a 7+ with 3, 4, 5 rings, correct? Tell me why chlorine is more likely to steal that electron. Right, Coulomb's law says that when these charges are closer together, there's going to be a stronger attraction between that negative and that. So that would be called electron affinity. So chlorine is going to release more energy when it steals that electron, whereas when iodine steals that electron, yeah, +7 is a super strong core charge, but it's so far away that it's going to be a lot less attracted to that negative. Questions on that? So again, it's not very uncommon for metals to have completely opposite properties of nonmetals. So metals get more reactive as you go down, whereas here, the nonmetals actually get more reactive as you go up. Metals get less reactive as you go to the right, whereas on our periodic table, as you go to the right in the nonmetal section, as they're adding that core charge, they'll get more reactive until you get to which column? Column 18, the noble gases. They don't have room to steal electrons, so they're probably not going to react very easily. All right, now when you compare the reactivity of the nonmetals with the electronegativity series on the back of the periodic table, how do they compare? Let's go ahead and pull up that periodic table. So now we're looking at this electronegativity series. And what was our most reactive nonmetal that we dealt with? Chlorine, followed by bromine, followed by iodine. So you can see there's definitely some elements that we did not look at up here There's a reason we did not use fluorine. I'm leery enough to use chlorine. It's a little dangerous making that chlorine gas in the fume hood there. I would not want to go anywhere near fluorine. I mean, that would be some pretty nasty stuff. Any questions? All right, well, let's go ahead and take a look at the rest of our activity. So I think we pretty much wrapped up station 3. Any questions on that? Samantha, you're still able to kind of follow along with what we're doing up here? Cool, good. All right, station number 14. This was just a qualitative lab, looking at similarities or differences. I forgot where I left off again. Yeah. No, it was group Tobin. Yeah, group Tobin. So group 6, what were some of the differences and similarities between these reactions up here?
I think group 5.
Sorry, yeah, group 5. Yeah. Question 15. What were some of the similarities and differences? Yep.
They're all like foggy.
Yeah, they form some sort of foggy, cloudy precipitate. Good. Libby, on the way, can you pretend like you're an animal tracker and look for like drops of blood along the way?
Sure.
Okay, cool. Yeah, so they form solid precipitates because this solid precipitate would be silver chloride, this solid precipitate would be silver bromide, this solid precipitate would be silver iodide. So yeah, they form solid precipitates. This would actually be an example of a double replacement reaction. So it's almost like a square dance. We had sodium dancing with chlorine, and we had silver dancing with nitrate, because positives and negatives can swap places in water. They just form a new dance partner. So positive sodium joins up with negative nitrate, positive silver joins up with negative chloride. One of those new combinations is not soluble. It doesn't dissolve, so then it settles on the bottom. That's that cloudy white, maybe yellow, cream colored precipitate you saw start to form. So they're not going to form the exact same color each and every time, but it'll be pretty similar. That's it. That's station number 17. So again, not a lot happening there, but just to show you, if you know how one element reacts, you can pretty much predict, at least in the right ballpark, what the other elements are going to do as well. All right, station number 5. How do metallic and non-metallic oxides compare in their physical properties? Group 6, what state of matter are the metal oxides in?
Like a powder, so.
Yeah, solids. What color? Yeah, grayish white solids. And whereas the sulfur dioxide and nitrogen dioxide were what?
Gas.
They were gases. This was a clear gas, and this was kind of a red gas. Now, they didn't look like gases when you were testing them because, again, I had to do that reaction up here. The gas then dissolved in water to form the pH. All right, metallic oxides formed what sort of pH? Group 7.
Basic.
Yeah, they were basic, so they turned kind of bluish violet on the pH strip, so kind of blue to violet. Cannot spell today. Violet. So yeah, blue goes with basic, at least in this indicator, and therefore group 1, the gases formed what?
And acidic.
Yeah, red or orange acids. And again, that's why it's called acid rain. Those pollution gases, sulfur dioxide, nitrogen dioxide, get into the water, they form acids. So if we're doing that in this format here, same answers, basic and acidic. All right, group 2, the power of the periodic table allows us to predict properties for elements we haven't seen yet. You didn't get to test strontium oxide back in the lab, but what would you expect it to look like?
It'll be basic since it's a metal.
Yeah, when you put it in the water, it'll be basic. And if you were just looking at this substance, what do you think it would look like?
A solid.
Yeah, it's going to be probably a white solid. Well, that's easily testable. Let's just on Google look up strontium oxide. sure enough, here it is, and sure enough, it is a white solid. So again, the periodic table, the way it's organized, because strontium is very similar to calcium oxide, magnesium oxide, you would totally expect to get very similar properties. Cool. Any questions on that? All right, final two discussion questions. Number 19, based on all of your observations in this lab, of all the elements on the periodic table, which would you expect to be most reactive? Group 2, what'd you say? Okay. I thought you saw something even more reactive than calcium in the lab. For example, potassium, yeah, that was the most reactive element that we dealt with in the lab. On the periodic table, would there be something even more reactive than potassium? Tobin?
Lithium.
Okay, yeah, if you're going from the activity series based on voltage, so if we're going from an activity standpoint, the answer would be lithium. But again, unless you know that that list was on the back of the periodic table, I probably would not have predicted that. If we're saying going from sodium to potassium is more reactive,
I was gonna say FR.
right, a lot of people are going to want to go with FR, and there's a lot of reason for that, because francium has a 1+ core charge, and it's in the 7th energy level. 1, 2, 3, 4, 5, 6, 7. Here's this teeny tiny electron so far away from a really teeny tiny +1, that's probably just going to go flying right off the atom. It's going to take barely any energy to rip off that electron. Now, I have read some journal articles. First of all, it's really hard to prove this because there's only 1 gram of francium in the entire planet at any given moment. So we're never going to scoop up enough francium to really deal with it and react it. Just because out of the entire Earth, there's like 1 gram. And what do you notice about francium on the periodic table? It is in the bottom left. Is there anything special with the way its symbol's written? Sam? It's radioactive because its mass is in parentheses. So because it's so rare, even if you did have it, you wouldn't waste it. It's one of the most expensive elements on the periodic table. Because it's so rare, you're not going to waste it by chucking it in water to see what happens. Because first of all, you're going to be going to get a pretty big explosion, but you're also going to be exposed to all that radiation. So we're not really even going to deal with that one. If you had to go with a backup to francium, maybe from a real-life perspective, what would probably be the most real-life element that might be the most reactive? Runner-up to maybe francium. Let's say I said you weren't allowed to pick francium. What would you go with? Sawyer?
Potassium.
Okay. I can think of maybe 2 more things that would be even more reactive than potassium. CS and rubidium. So rubidium would probably be even more reactive than potassium, and I would guess CS would be even more reactive than that. So I would probably say on a test, depending how it's defined, lithium would be an acceptable answer from a voltage electrochemical standpoint. Francium, just based on these simple models, would be an acceptable answer, but a lot of people don't pick that because you're never going to deal with that. So I'd say cesium would be also a pretty good answer for one of the most reactive metals on the periodic table. So I'll give you some leeway there. Any questions on that? All right, group 3, based on all of your observations, what would probably be the most active or reactive non-metal on the periodic table? Yeah, probably fluorine. So again, from the electronegativity series on the back of the periodic table, yeah, that answer is definitely fluorine, F2. So when you're simply looking at an F atom, it's a 7+, and it's got 2 rings of electrons. So a super strong attraction to a negative being pulled in. We also talked about that when that electron goes in there, because it's going in a box that already has an electron, there's a fair amount of repulsion there. So I would also say chlorine would be an acceptable answer. So the back of the periodic table from that voltage standpoint is going to say fluorine. But because this is so small and you get some repulsion there, chlorine would be an acceptable answer from an electron affinity answer. Now, basically, the textbook answers are going to tell you it's fluorine and francium, basically opposite corners of the periodic table. But never, nothing's ever as simple as what we make it out to be in chemistry. So again, I'm giving you some other answers that would be acceptable depending how you explain it. So lithium and cesium would be acceptable for metals. I'd say chlorine would be a pretty good runner-up, if not maybe even slightly better than fluorine, just based on the fact that you have the less repulsions in fluorine. So with that being said, quick conversation in your small group about your new conclusion. When I call in your group, what one new or uncertain thing do you guys want to share?
We just said
But then the rest is too much about stress or just one. This one is kind of great that we tested the most interesting
All right, sounds like we're wrapping that up, so let's go ahead and reverse order. Group 7, what's one of your new or uncertain items?
We had said maybe test other metals, either like lithium or beryllium, is it? FR?
Oh, francium? Okay, yeah, I could definitely do lithium. I have lithium in the back room there. That would be interesting. And why am I not going to do francium?
Because it's radioactive.
It's radioactive, and where would I get francium?
You can't.
You can't. I mean, you're going to go over the entire Earth, scoop up all the dirt, stick it in a blender, and extract all the francium, and at most you're going to have 1 gram, but it's going to decay pretty rapidly. So, yeah, francium, I mean, yeah, it's not going to be possible. But, yeah, I would expect it to be pretty reactive. All right, group 6.
You said you test some metals that have orbital.
Oh, the rare earth elements, yeah, so the lanthanides or actinides, cool. Yeah, I'd have to see, I don't know if we have many of those pure elements back there. We have some europium compounds in the back room. We have neodymium magnets, but yeah, I'm not sure if we have actual pure lanthanides or actinides. I'd have to check that. Maybe I'll do that during flex. Yeah, that would be interesting. A lot of times they're going to act very similar to the elements in column 3. So scandium, yttrium, all of those Fs kind of squeeze into that column 3 there. Yep. Good question. Mm-hmm.
How do we discover francium?
How do we discover it?
If there's so little of it, like how do we know it's a thing?
How do we know it's there? So that's an excellent question. So as we definitely have elements bigger than that. So as we're looking at those synthetic elements, as they start to decay, they're probably going to turn into francium. So maybe in a particle accelerator or some of those nuclear isotope reactors, we would probably see a line on a graph that has a mass of 223. So we know there has to be some isotope there. And we know that there's an atom out there that does have 87 protons, and we can test for that with X-ray diffraction. But yeah, you're never going to have a group of those atoms together. So at most, we're talking about a couple atoms at a time, giving you a little blip on a computer screen. Yep, good question. Group, I think we're 5. Something new, something uncertain.
They said that you could test the elements in cold or boiling water to see how it affects the reaction.
Oh, yeah. Interesting. And how would you think hot water would affect them? Probably a lot faster. Yeah, there's a whole chapter about kinetics and AP chemistry, and we do reactions like that to see how much faster. Can you mathematically quantify that? So that's all kinetics or reaction rates. Yep, good. Group 4.
I said for new, use a bigger piece of potassium with water for a bigger reaction.
Bigger piece of potassium. Yeah, I'd want a much bigger, I would want to do that outdoors. I'm sure you can see all sorts of crazy people on YouTube. I'm not condoning this, but I'm sure there's YouTube videos out there about sodium and potassium. I know there's some even, I think I showed it when we went over the graphing, the coloring periodic table activity. I showed you a video with rubidium and cesium. Cesium broke the beaker that it was in. So yeah, you got to be really careful with some of that stuff. Group 3, something new or uncertain.
Test the metalloid and see how it reacts.
Metalloid, oh, that'd be interesting. Yeah, I definitely have some boron in the back room, not aluminum, silicon, germanium. Yeah, they're going to have some in-between properties. I'd say as far as their reactivity goes, they're going to be more similar to the nonmetals, but they're going to be way less reactive than the other nonmetals because, again, they're just starting to get into that high core charge of maybe +4, +3, +4, +5. So they're kind of moderately strong core charges. Yep, good. Group 2, something new or uncertain. You guys got some real good questions here.
I was like wondering like how you determine station 3. Like, only did a few, but like how you determine if it's less reactive or reactive.
Okay, so that's a really important concept. So which element wants to be by itself? The more reactive element or the less reactive element? So if something's very reactive, it's okay just kind of hanging out? No, it's going to react with something. So it's the less reactive element that wants to sit by itself. And how did we know which was the less reactive element? Would you agree you added the hexane layer and the element that was by itself worked its way up into that top layer? So that's why in that column that says what was the color of the top layer and what element was in that top layer, we cared so much about that top layer because that was the element that was less reactive, which means the other element by default had to be the more reactive element. Does that make sense? Okay, cool. I'll take that right there. Thank you.